auto bridge in the world. 2 parallel roadways spanning a lake 24 miles wide. Made entirely of thousands of prefabricated parts. Hidden in each span, the techno secret of the bridge's success. An engineering breakthrough that made possible a record-setting triumph. Now, the Lake Pontchartrain Causeway on Modern Marvels. In the land of voodoo and Mardi Gras, jambalaya and zydeco is an engineering marvel that seems to go on forever. Head toward the lake and drive onto a concrete span, one of 2 that crosses the largest inland body of water in Louisiana. Speed along the highway, 2 lanes in each direction, toward the north shore of Lake Pontchartrain, and you'll lose sight of land in all directions. That's because at the 12-mile mark, you've only reached the halfway point on what is the longest overwater highway bridge in the world. The bridge actually traverses roughly 1/1000th of the Earth's circumference. Whatever the causeway may lack in visual flamboyance, it makes up for in engineering and endurance.
The single most important thing about this bridge is that it is 24 miles long, and it was built using manufacturing methods where they built modular beams and piles and pile caps and slabs in a very mechanized way.
The beauty of the causeway is in the eye of the beholder. The parallel span stretching out to where you can see no land anywhere in sight is a beautiful vision with the background of one of the most beautiful sunsets in the world.
These 2 roadways are 84 feet apart. On any given weekday, as many as 30,000 vehicles can pack onto these concrete trestles, made up of thousands of separate precast sections. As cars speed across from New Orleans to the south and Mandeville to the north, large boats and barges pass under the bridge 8 miles from the north shore. A bascule, or drawbridge, lifts 4 steel grid sections of road called leaves, nearly vertical.
When we turn on the lights to the gates, you can't do this out of sequence. It has a fail-safe mechanism to keep it from just opening automatically. The gates lights have to come on, then the gates have to come down, and then we can release the emergency brakes here and mash the raise buttons. This is for the northbound spans.
The procedure to raise the southbound leaves is identical. Smaller boats can pass beneath 2 matching raised sections of the causeway called marine spans, which provide 50 feet of vertical clearance. 3 sets of smaller marine humps provide 25 feet of vertical clearance. Smaller pleasure boats simply pass under the roadways, which normally have between 15 and 16 feet of vertical clearance. At its highest point, the bridge's roadway is never more than 60 feet above the water. 7 turnouts spaced along the spans provide a safe haven for drivers with breakdowns, or for people who decide to go back the way they came. But there are no breakdown lanes on the bridge, although the causeway's guardians can lend a helping hand.
Our maintenance department is responsible for 3 roadways, or 3 arteries that enter into the bridge going southbound. We assist motorists with flats, wrecks, accidents, things like that. We don't issue tickets. We're mostly there for assistance.
Northbound commuters get a free ride, but the southbound lanes are hit with a $3 toll, which can be paid in cash or charged using a tagging system. Just don't try to blow by the toll booth on your way to the French Quarter.
Yeah, they got cameras around. They got the police that monitors and stuff. Like if somebody was to run the lane, we would call it in on the radio and they would get them.
There's no place to hide on a 24-mile concrete slab in the middle of a lake.
Once you go out there 8 miles, you can't see anything but water. You're over the horizon. You can't see New Orleans anymore, and you damn sure can't see Mandeville at all. And for the next 8 miles, you're completely surrounded by water, and you can't see anything by water because everything's over the horizon.
Being surrounded by water on the causeway is a little like living in southern Louisiana on the Mississippi Delta, a region that is nearly surrounded by huge bodies of water. Consequently, bridges have always been a necessity around New Orleans. In one direction is the Gulf of Mexico, in another, the mighty Mississippi, and in another, brackish Lake Pontchartrain. The lake is actually an estuary off the Gulf of Mexico, with an average depth of between 10 and 16 feet. But at 610 square miles, it was always a significant travel barrier between the north and the south. The landmass described by these water boundaries is known as the Isle of Orleans. Drainage had been a problem since the city was founded in 1718, well into the 19th century.
You might think about New Orleans as half of an oyster shell. And along the river, the ground is higher because when the river overflowed every year, there was a sedimentation process. And the part that would dry up last as the floods receded was right next to the riverbank.
During the region's many torrential rains, city dwellers have always escaped from low areas, moving toward the river, or better still, across the lake where the land is high, far from the lurking danger of stagnant, polluted water. The ever-looming threat of a flood actually hastened the need for a bridge as an escape route during the city's past.
There was inadequate municipal sanitation, so there would be outbreaks of cholera, typhus, and other diseases. So New Orleans was thought of as unhealthy, and if you could get out of the city in the summertime, that was the thing to do. And you could tell by reading the newspapers in June when they started talking about how healthy it was, that something terrible had broken out, because they knew once everybody left there wouldn't be any advertising.
The place to go was, and still is, across the lake to the North Shore. Towns like Mandeville and Slidell and Madisonville were known for their pine-scented fresh air and their spas. But there were no quick and easy ways around the massive lake. Depending on the route and the conditions, an automobile journey might take 4 or 5 hours. Ferry service was inconsistent, expensive, and sometimes dangerous because of potential squalls on the lake. Although some operators had periods of modest success, none of the ferries lasted. Many people chose to stay put rather than brave the journey in the oppressive heat. But as the automobile revolutionized transportation in America, the people of Louisiana began to look upon Lake Pontchartrain as a hurdle to be leapt, rather than a wall to be flanked. During the flush years of the mid-1920s, dreamers in and around New Orleans began proposing schemes to bring automobile traffic to the North Shore of Lake Pontchartrain. Some of these ideas were more ambitious than they were realistic.
There was a proposal on the North Shore in the 1920s to build a causeway to New Orleans. And what they planned to do was to dredge a series of islands and then build bridges connecting the islands. And once they had the islands in place, they would subdivide them, sell the lots, and that would pay the cost of the project.
Well, lo and behold, this was moving ahead. They'd sold stock, and then all of a sudden, 2 guys named Watson and Williams came along, and they said they're going to build a toll bridge at the other side of the lake.
Watson and Williams planned a 7-mile bridge across the eastern end of Lake Pontchartrain using a simple concrete structure.
But the effect of building this bridge was to knock the props out from under the people who were going to build the series of islands, and that collapsed.
That the 25 or more million American families.
Populist Louisiana politician Huey Long opposed the concept of a toll bridge and campaigned vigorously against the Watson and Williams toll bridge during his unsuccessful run for governor in 1924. When Long finally won the governorship 4 years later, the Watson and Williams Bridge was open for business, charging $1.25 per car. Long promptly built a free bridge just to the east of the Watson-Williams Bridge. All these bridges still stand.
And incidentally, that put the Watson-Williams Bridge Company out of business. And the state bought the Watson-Williams Bridge for cents on the dollar.
The results of these and other bridges cutting shorter paths across the lake was a quicker commute. Now the lake could be traversed in as little as an hour and a half. But none of these other bridges dared to cross straight down the middle of the lake, as the Bold Island scheme had proposed. It was not until the mid-1950s that a new scheme for crossing Lake Pontchartrain would gain momentum. It was driven as much by new technology as by demand for a bridge. More than 5,000 years ago, melting polar ice caps raised the sea level in the Gulf of Mexico, creating what is now Lake Pontchartrain. The Lake Pontchartrain Causeway will return on Modern Marvels. The story of the Lake Pontchartrain Bridge is the story of pre-stressed concrete technology. In the 1950s, Maxwell Upson of the Raymond Concrete Pile Company of New York began conducting research on pre-stressed concrete. Pre-stressed concrete was a new and largely untried construction method for such large projects, at least in the United States back in the late 1940s and early 1950s. Concrete, that ubiquitous mixture of cement, sand, gravel, and water, by itself has structural weaknesses.
If you were to make let's say a concrete plank, let's use that as an example. Let's say you made one 20-foot long, and you went to one end and you picked it up real quick, it very likely would break in the middle.
Because concrete has high compressive strength, it can withstand forces that push it together without fracturing easily. But because concrete has low tensile strength, in other words, it can't easily withstand forces that pull it apart, it will crack. Pushing forces on the top have no effect on the plank, but pulling forces on the bottom crack it. To solve this problem, the construction industry relied on laying steel rods inside the concrete, creating what is known as reinforced concrete. Steel rods have great tensile strength, so that when the hardened concrete plank is lifted, weight is shifted to the rods. Although some cracking of the concrete is inevitable, pre-stressing improves on this method by adding tension to the slab.
I'll give you an analogy first. If you took a set of books and you put them cover to cover and try to lift them up, you couldn't lift them up unless you took your hands, put your hands at the ends and pressed the books together. Well, that pressing is actually what happens in a pre-stressed concrete beam.
Pre-stressed concrete uses very strong steel cables or wires stretched inside the form where the slab will be poured.
You hold them at one end and you jack them under high tensile strength at the other end, then you pour the concrete. After the concrete has set, you cut the wires loose at each end, and they put the whole beam into compression. Then you can pick this beam up, and it never goes in tension on the bottom, never cracks.
The first major pre-stressed concrete bridge was built in Philadelphia in 1949. It's the Walnut Street Bridge. This bridge came along while pre-stressed concrete bridges were undergoing a lot of development.
The Walnut Street Bridge proved to American engineers that pre-stressed concrete could be used for large public works projects. Other bridges would follow.
I had a call from Maxwell Upson, and that was almost like getting a call from one of the disciples. He was one of a handful of the most highly regarded engineers in the construction industry. He had invented several different types of concrete piles used all over the country and the world. And this was his latest invention, a pre-stressed cylindrical concrete pile.
The pile Upson invented was essentially concrete and steel. Upson applied the pre-stressed technology to concrete pilings. Pilings are the round supports found on bridges and foundations that carry structural load and keep structures from collapsing. But they can only be prefabricated or precast so big before they become unwieldy. Before Upson's successes, 24 inches in diameter had been roughly that limit.
So Upson came along and he said, look, why don't I make a bigger pile, make it round, and make it hollow, and then pre-stress it.
Raymond Concrete Pile Company, under Upson's direction, adopted a revolutionary method called the Senviro process to produce hollow pre-stressed concrete piles with a circumference of 54 inches. The Sen in Senviro stood for centrifugal force, which made the concrete spin to the outside wall of the piling form. Vi stood for violent vibration that compacts the concrete, and Rho stood for rollers that roll the concrete hard against the outside form.
After the concrete is placed in the pile, then it's spun at a higher speed to compact the concrete and also to remove any excess water.
The less water, the stronger the concrete. Upson's Senviro process could make concrete that could withstand pressures up to 10,000 pounds per square inch.
So Upson said, let's do this. Let's take a 16-foot long pile or section, and let's put longitudinal holes in the walls. Then when you want to make a pile, you bring up several of these sections. You line them up on a rack so that the holes all line up. Then you run high-strength steel wire through those holes. At the far end, you clamp something to hold it, and that will push against the pile. And at your end, you put jacks to also push against the pile, and you start to work these jacks, and you compress the pile.
After the other end of the pile is plugged, wires are cut. Grout is then fed under high pressure into the holes of these post-tension piles. Now the piling is pre-stressed. The seam is sealed where the piles fit together. Mud or silt fills the hollow piles when they're driven into the ground. Upson had invented a very efficient way to make strong, wide, and long pre-stressed concrete piles, good for resisting erosion and water. And there were two obvious applications. One was for platforms in the relatively new offshore oil drilling industry. The other was for highway construction, which went into overdrive under the new Eisenhower administration. The 30-year-old dream of spanning Lake Pontchartrain suddenly seemed a real possibility. A consortium of business interests formed the Louisiana Bridge Company. Their goal was to win the bid from the New Orleans Expressway Commission for construction of the causeway.
By 1954, the legislature created the Greater New Orleans Expressway Commission that was to operate the causeway, and it was that commission that actually issued the bonds. And it was a remarkably successful illustration of local political cooperation. I can remember when I was a kid, and one of the officials was talking to my father, and he said, if this thing works, we're going to make a lot of money. And if it doesn't, we're going to lose our shirts.
In 1955, the Louisiana Bridge Company began work on what would become the first Lake Pontchartrain Bridge. The Bridge Consortium built a concrete casting facility right on the lakeshore, where the span of the bridge would reach its northernmost point.
They bought 40 acres on the shore of Lake Pontchartrain between Mandeville and Lewisburg. And then they dredged a 1,200-foot long canal that was 151 feet wide. It was 12 feet deep. And they precast the sections on the land.
The canal enabled boat and barge traffic to deliver raw materials and manufactured sections of the bridge right into and out of the plant. Much of what was produced at the plant would be too massive to move over land. Owning a manufacturing plant right next to the site of the causeway allowed the Louisiana Bridge Company to build what was essentially the world's first prefabricated bridge.
The main difference between this bridge and other bridges is the manufacturing plant was built especially for this bridge. So it was laid out in a very optimal way to manufacture all the components of the bridge in the most efficient way.
In addition to the pilings, the piling caps and the roadway slabs would also be made of concrete at the job site, then pieced together on the lake.
And it was built like a big tinker toy. We would cast the piling, cast the caps, and cast the slabs, take them out in the field and put them together.
The first pilings were sunk on May 23, 1955, 4 months after manufacture began in the yard. With the clock ticking on the 24-month construction contract, the company now had less than 2 years to complete the longest bridge ever built. The Lake Pontchartrain Causeway has become a key stop for more than 200,000 purple martins on their annual migration from Canada to South America and back. The birds roost in the understructure of the bridge. The Lake Pontchartrain Causeway will return on Modern Marvels. Throughout 1955 and much of 1956, prefabricated concrete sections of the Lake Pontchartrain Causeway were being poured, cured, barged, and installed by a team of engineers and workmen numbering over 200. The process began with the 54-foot-long concrete slabs, the caps, and the pilings.
The slabs are first constructed in a bed in the manufacturing plant. The bed is actually a form for the concrete for the slab. The bed is able to accommodate 8 slabs lengthwise and 3 slabs across. So at one time they were able to make 24 deck slabs.
Reinforcing bar mats were placed in the slab bed, and tendons on the mats were pre-tensioned. Then concrete was poured over the mats.
After the concrete was poured, it was finished on the top with a finishing machine, and then it was cured. It was actually steam cured. They moved enclosures over the slabs and introduced steam into the enclosures to cure the slab.
Steam curing the concrete slabs sped up the time it took for the concrete to set up or dry. Slabs that would have taken about a month to cure could be done in about a week. Then the steel tendons would be cut, and the slabs moved to a storage area for additional curing. There, the slabs would sit for about 2 weeks until they were transported out onto the lake.
Then you had a pre-stressed slab, and that's the way they were made, mass-produced, loaded on a barge, hauled out, set in the bridge.
Pilings were paired along the path of the bridge where 2 sections of roadway slabs were joined together. Here at these junctures, called bents, a prefabricated concrete cap would fit over the 2 pilings below and create a connection for the 2 slabs on top. The first step in the process was driving the 88-foot-long pilings roughly 70 feet through the Louisiana mud.
Barge-mounted cranes would lift the piles, the pile cap, and the slab sections into their place. Piles, of course, were lifted up and then driven down through the water, through the bottom of the lake, using a steam pile driver, assisted by water jetting.
Raymond had a history of designing and building their own highly specialized construction equipment. Raymond went to work with developing the pile driving hammers to be used. They would drive 2 piles for every bent. Then they'd move ahead, drive 2 more piles, and move ahead and drive 2 more piles.
The pile drivers were never able to punch the piles into bedrock because there wasn't any to be found.
There is no rock around here. The only rock down here may be about 20,000 feet deep. You find it when you drill oil wells. The pilings are sitting in a very, very hard sand strata. Sand is a very, very good foundation material, confined sand, I might add. It's very dense, and of course you gain friction on the sides of the pile, creates a tremendous amount of load-bearing capacity.
The hollow cylinder 54-inch diameter piles had surprisingly thin walls, only 4 5/8 inches thick. But the concrete was so dense because of the synviro process that it was exceptionally strong, even in the brackish water of Lake Pontchartrain, an environment hostile to concrete. After the piles were driven and the tops sawed off to a consistent height, another team would fit the multi-ton caps onto them using a large crane. This was a delicate operation requiring man and machine to work together with precision. One mistake, and the crane could easily crush a man. After the caps were in place, the final piece of the puzzle was brought in and mounted on top.
The big slabs were set with an A-frame derrick. And at that time, the slabs weighed about 200 tons.
Metal shims were used to achieve a perfectly level roadway. The slabs were mounted onto steel posts in the caps. Each slab was like every other, each cap identical, every piling the same. 8 miles from each shore, the drawbridges offered even greater clearance. Here, the bridge sloped up elegantly. The bascules raised the leaves using a pendulum-like mechanism and a small engine. A weight counterbalanced the weight of the leaves so that when the engine supplied a small force to the counterweight, the leaves would raise as the weight sank. Eliminating that force brought the leaves back down again. Other than the bascules, a single turnaround utility road, and the periodic rises, all the bridge components were uniform. There were no significant delays or disasters, and the process went like clockwork.
You could just every day go out there and look, and they were further across the lake.
In a sense, it was prefab. But the prefabrication was something of an engineering marvel, too. And so it was basically a very simple operation, and they moved with remarkable speed. And they finished the project 4 months before they had expected to.
After 14 months and $30,677,000 added to the $21 million for the purchase of the land, the Lake Pontchartrain Causeway was completed. It opened on August 30th, 1956, to great public fanfare. The two-lane highway trestle bridge used 2,243 precast panels, each 33 feet wide and 56 feet long. It stretched for 23.86 miles across the middle of the lake.
There was a ribbon cutting at the south end, and then there was a motorcade that was supposed to be single file across the causeway to the north end, where there would be more ceremonies. When they got to the north end, there were so many cars that there was no way for them to get off, so the cars were backed way up on the causeway.
From that very first traffic jam, demand for the bridge, which cost $1 to cross, was immediate and overwhelming. New Orleans was now 29 miles and 40 minutes closer using the causeway. People could commute from their homes in St. Tammany Parish on the North Shore to their jobs in New Orleans. Housing grew. Traffic grew.
It certainly gave industry and commerce a boost, and it also provided another evacuation route out of the city of New Orleans, which most people will tell you is most prone to hurricanes and is least prepared.
Within just a few years, the causeway was overwhelmed with an average usage of 3,000 cars per day. After examining its options, the Causeway Commission soon realized there was only one sensible solution. It needed to build another bridge across Lake Pontchartrain. Waterspouts, a type of tornado that forms over bodies of water like Lake Pontchartrain, occasionally hit the causeway, but haven't caused structural damage. The Lake Pontchartrain Causeway will return on Modern Marvels. The Lake Pontchartrain Causeway was such a success that within a few years it was nearing capacity. Although people considered the bridge a boon, it had its drawbacks. The two-lane highway provided no safe zone for breakdowns, and the narrow roadway could be hazardous in fog. Head-on collisions were also a danger. Preparations for another bridge went swiftly during the mid-1960s. The Bridge Consortium's adjacent yard was still operating, having been kept busy with other local bridge assignments since the first span was completed. Further, engineers only needed to look at the full-scale model sitting out in the lake for a template in designing a second bridge. A new span begun in September of 1967 would attempt to address some of the drawbacks on the first span. But there was no question that the prefabricated construction method would be used again.
Everything had been tested and tried and worked out, and the equipment was all there. There was one major improvement. And if you ever get cocky about thinking you've done something, don't, because somebody's going to come along and find a better way. Somebody, I don't know who, came up with the idea, let's put 3 piles in a bent.
Slabs, which on the first span had been 56 feet long, would be 84 feet long on the second span.
So that you're not using any more piles in the total structure, and you haven't increased the cost, but you made it a lot stronger.
Which meant that every third joint you matched up with the old bridge. And that was a big help in laying out the bridge in the field. And that was the purpose of it.
The change in the size of the slabs actually made their manufacture more cost efficient. But because of the increase in size, the barges and the cranes used to place them on the bridge all had to be larger than the ones used on the first span.
These bridge sections weigh almost 300 tons apiece. And one way you can transport them, and that's on a barge. So everything has to be done on the water. This kind of bridge can't be built on land because you can't truck something that weighs 300 tons down the street. And the cranes we had were very large Clyde Whirley cranes and big A-frame cranes.
With the yard producing as many as 20 slabs in 7 days, at times the workers out on the lake were able to lay down over 1,600 feet of bridge a week. Consequently, construction moved even faster than it did on the first span. The new pilings were manufactured with a slightly improved, thicker 5-inch wall over those in the first bridge.
They used a little thicker wall to get a little more cover over the reinforcing bars so that they had better resistance against salt attacking the reinforcing bars.
The quality of the steel and the concrete had advanced in the decade between the first and second bridge construction. A humping or bowing in the concrete caused by the release of stress in the pre-stressed slabs was partially responsible for a somewhat bumpy ride on the first span. Engineers factored that bowing into the newer slabs.
We made a real good job of putting a little sag in that bridge and making it come out flat. In fact, that's what I did. I used to calculate all those things when I was working with them, and I made all the drawings for it.
With 2 spans, the engineers were able to create 7 connecting alleys, or crossovers, at intervals along the roadway.
They had anticipated that because the bridges were 84 feet between them, and one of those spans would just fit in there.
But as smoothly as the second bridge went up, the process wasn't entirely without incident.
I remember one time I was out there and the gnats were so bad that we thought we were going to have to quit working.
We had a storm that hit us one afternoon with 80-mile-an-hour winds. And you're talking about hurricane-force winds. And we knocked down a little piece of the bridge in the process. Some of our barges got loose.
Sometimes the incidents were more than aggravating. They were tragic.
We were setting a cap on the piling one day, and we would cast these caps upside down. And in that shape upside down, there was reinforcing sticking up that would eventually project down into the piling. And on the job, they would take cables and rotate these over. And one day the cables slipped. They had rigged it slightly wrong. And this one guy got both arms and both legs cut off.
Despite various injuries and 2 deaths, construction of the second bridge was remarkably efficient and cost-effective. The total price tag came in at $26 million, which was $3 million less than the first span.
The second bridge actually ended up taking a little longer than the first bridge. It took 25 months, but it was still several months earlier than the schedule for that bridge. They also did some work on the first bridge. They made a few changes.
Both of the bascules in the old bridge were replaced to meet new navigation regulations. The northern bascule was raised even higher, and the opening widened to 125 feet. A matching bascule was included in the second bridge at the same location. The southern bascule was removed entirely and replaced with a channel crossing that provided a 45-foot clearance for boats and barges. It also had a matching crossing in the second bridge.
We had to finish the new bridge completely and then tear out part of the old bridge and raise it up and rebuild part of the old bridge. So it was pretty tricky.
On May 10th, 1969, the new 4-lane Lake Pontchartrain Causeway opened, with the easternmost span sending 2 lanes of traffic north and the westernmost span sending 2 lanes of traffic south. There was one notable difference between the otherwise twin spans. The new span was 1/100th of a mile longer, at 23.87 miles, than the old one, making it the longest in the world. From the moment the second span opened, bridge traffic has steadily climbed. Soon the causeway simply won't be able to handle the projected increase in traffic. Not surprisingly, talk has already begun on what kind of bridge the third causeway should be. To compensate for the curvature of the Earth, the Lake Pontchartrain Causeway was built roughly 2 inches longer than the distance it spans. The Lake Pontchartrain Causeway will return on Modern Marvels. With over 50 miles of roadway, a police force of 18 full-time officers, and thousands of commuters driving by every day, the Lake Pontchartrain Causeway in some ways resembles a small town. The 117-person staff that monitors the bridge has many responsibilities.
Seems as though tailgating and speeding is our biggest concern out here. We do our best with the traffic, though, and with the bridge not having any shoulders, and during our peak hour, it's hard for our units to get out, and it becomes very hectic.
A $6 million 15-sign message board system warns motorists of traffic conditions.
Instantly, the signs would then change and say there's a breakdown ahead, merge left or right, whatever the case may be. And we also have our own radio station, and we're able to tell our motorists to tune to that station, and we can give them safety information and instructions.
102 call boxes line the bridge in both directions. These safety precautions have contributed to the causeway's admirable safety record. But accidents still occur, although not necessarily on top of the roadway.
There are a number of things that can happen when a marine vessel strikes the causeway. It can strike the pilings. These pilings are made to hold a load on top of them. They're not made to take a side strike. So a barge of weight significantly could damage and dislodge a slab or two or more. It also could get under the bridge and in heavy wave action lift a span. It could get in between the two bridges, and it could move for several miles, impacting a number of pilings.
Although rare, these collisions have occurred 16 times over the life of the two spans. A number of the 55 travelers killed since 1971 died when their cars drove off the bridge. The original engineers could not have practically designed the bridge to withstand these impacts.
You're talking about a 300-ton barge going at 2 or 3 knots, and you want to stop it in 6 inches? Forget it, man. You know? Not going to happen.
However, the bridge builders did anticipate such collisions and fitted the causeway with a number of spare parts.
On both sides of the bridge, you'll see a piece of bridge sitting out there in the lake, all built and finished. And you'll see pilings sitting out there, and you'll see pile caps sitting there, and you'll see rigging and big spreader bars that we use to pick the slabs up with, all sitting there. A contractor with big equipment can move in, and if they know what they're doing, they can have that bridge open back in a matter of days.
But the causeway isn't just sitting around waiting to be struck by a barge.
We have a radar system out there now that if you get within 1 mile of the causeway bridge, an alarm will go off. We're aware of it, and we can actually project a potential striking point on the causeway.
Back on the asphalt, the causeway puts a priority on the safety of its passengers, using a fleet of vehicles, including a truck with a rescue basket for people who may have gone over the side into the lake.
We like to say we're the world's longest and safest bridge. At this point, we're about to enter our 3rd year without a fatality, and we had a wonderful stretch of no fatalities from 1986 to 1991. So we've been in the forefront in the bridge industry as far as safety is concerned.
Despite the causeway's impressive safety record, thick winter fog can wreak havoc, and winds of 50 miles an hour will shut it down. A team of safety officers and maintenance vehicles can be deployed to convoy travelers through the fog or quickly drag them off the road after a breakdown.
We keep up over 80 police units and over 30 maintenance trucks, and some other small equipment such as tractors and some six-wheelers and different things we use on our grounds work. Well, we put quite a few miles on them.
The crew also has a specialized vehicle for monitoring the day-to-day health of the bridge itself. Called an underbridge inspection unit, it's actually a highly specialized 35-ton crane with a 50-foot extendable boom.
It'll get us anywhere on this 24-mile bridge that we need to go. From the tallest of the humps to the lowest area, it'll get us anywhere. It'll go from one side to the other. We have to do an inspection of the entire bridge, and myself and one other engineer will ride, and we'll look every inch of the bridge. We're looking at piling, caps, the girders, the spans, any part of it that they want to look at, they're inspecting. We have to do this once every year, which takes approximately anywhere from a month to a month and a half to do.
The causeway is also undergoing a multi-million-dollar structural maintenance program designed to prolong its existence, with an emphasis on the 50-year-old pilings that make the spans an engineering marvel.
The lake is brackish water, and the brackish water attacks concrete. The sulfides in there attack the cement, and you do get some erosion, particularly at the wash line.
We inspect those to see what repairs that need to be made, such as hairline cracks that are repaired by epoxy repairs of those cracks. Some of the more severely damaged piling are totally encapsulated with a fiberglass collar.
We typically have about 3 crews out there, totaling about anywhere from 17 to 20 people. One crew will clean the marine growth off of the piling using anywhere from 6,000 to 10,000 psi water blasting above and below water. The second crew, the way we've got it worked, sets a 1/8 inch thick fiberglass jacket that stays in place. And then the third crew basically comes behind them and pumps an underwater epoxy grout into the fiberglass form that stays there.
As crews work to maintain the existing spans, others wrestle with long-term plans to deal with the ever-increasing bridge traffic, which is projected to reach capacity by 2018. Despite discussions of such exotic alternatives as a magnetic levitation train, a third auto span seems inevitable.
What we would do is build a third span, and it would have a shoulder on it. So you would have, on the new span, you would have 2 lanes and a safety lane. Then you would leave the middle lane alone.
On the original 1956 bridge, the sidewall barrier would be removed and a shoulder would be added. This would provide 2 lanes of traffic on the newest span going one direction with a shoulder, and 2 lanes of traffic on the oldest bridge going another direction with a shoulder. The middle 1969 span would have 1 lane and a shoulder lane. This bridge could alternate directions depending on usage.
That would give us 3 safe traffic lanes coming south in the morning, and the middle one would be reversed, 3 safe lanes in the afternoon peak hour traffic.
More than likely, the new span will be similar in design to the earlier spans. Just clean lines running parallel across the lake for 24 miles.
I love to go across it. I love to drive on it. You know, I think about all the people that were there and, you know, the things we went through, the guys we worked with. But we had people. God, we had people in that. We had skilled people. We had good people, you know. We had real hard-working guys. We had people that were a lot of fun to be with.
Those hundreds of workers employing the new and largely untried technology of pre-stressed concrete made these deceptively simple bridges a reality. Their Lake Pontchartrain Causeway proves that simplicity can be style and that straight lines can be sublime. Auto bridge in the world. 2 parallel roadways spanning a lake 24 miles wide. Made entirely of thousands of prefabricated parts. Hidden in each span, the techno secret of the bridge's success. An engineering breakthrough that made possible a record-setting triumph. Now, the Lake Pontchartrain Causeway on Modern Marvels. In the land of voodoo and Mardi Gras, jambalaya and zydeco is an engineering marvel that seems to go on forever. Head toward the lake and drive onto a concrete span, one of two that crosses the largest inland body of water in Louisiana. Speed along the highway, 2 lanes in each direction, toward the north shore of Lake Pontchartrain, and you'll lose sight of land in all directions. That's because at the 12-mile mark, you've only reached the halfway point on what is the longest overwater highway bridge in the world. The bridge actually traverses roughly 1/1000th of the Earth's circumference. Whatever the causeway may lack in visual flamboyance, it makes up for in engineering and endurance.
The single most important thing about this bridge is that it is 24 miles long, and it was built using manufacturing methods where they built modular beams and piles and pile caps and slabs in a very mechanized way.
The beauty of the causeway is in the eye of the beholder. The parallel span stretching out to where you can see no land anywhere in sight is a beautiful vision with the background of one of the most beautiful sunsets in the world.
These 2 roadways are 84 feet apart. On any given weekday, as many as 30,000 vehicles can pack onto these concrete trestles, made up of thousands of separate precast sections. As cars speed across from New Orleans to the south and Mandeville to the north, large boats and barges pass under the bridge 8 miles from the north shore. A bascule, or drawbridge, lifts 4 steel grid sections of road called leaves, nearly vertical.
When we turn on the lights to the gates, you can't do this out of sequence. It has a fail-safe mechanism to keep it from just opening automatically. The gates lights have to come on, then the gates have to come down, and then we can release the emergency brakes here and mash the raise buttons. This is for the northbound spans.
The procedure to raise the southbound leaves is identical. Smaller boats can pass beneath 2 matching raised sections of the causeway called marine spans, which provide 50 feet of vertical clearance. 3 sets of smaller marine humps provide 25 feet of vertical clearance. Smaller pleasure boats simply pass under the roadways, which normally have between 15 and 16 feet of vertical clearance. At its highest point, the bridge's roadway is never more than 60 feet above the water. 7 turnouts spaced along the spans provide a safe haven for drivers with breakdowns, or for people who decide to go back the way they came. But there are no breakdown lanes on the bridge, although the causeway's guardians can lend a helping hand.
Our maintenance department is responsible for 3 roadways, or 3 arteries that enter into the bridge going southbound. We assist motorists with flats, wrecks, accidents, things like that.